So this is a combination of all three. So we've had rotational spectroscopy, Rovibrational spectroscopy, and now we add on electronic. So we have all three transitions happening at the same time. And we're only able to really resolve the electronic and the vibrational in this lab, though. If we had a high-resolution laser, we might be able to resolve the rotational lines. So they're there, but they're just not resolved. So all the peaks are smeared together. And so we'll look at this. This lecture today is essentially a lab lecture. It's based on what you're going to be doing in the lab this week. So this will help this week's lab be more enjoyable. So we have these electronic potential energy surfaces here, and then we also have these vibrational levels. And we're looking at transitions between both. So we have an electronic transition, which puts it into the visible region. So this is a UV-Vis experiment. And then we have lots of little peaks on our spectrum. We wouldn't resolve those unless we scan really slowly. So we set the resolution of the spectrometer to its highest setting, which meant we had the narrowest wavelength of light coming through the monochromator, which means we didn't have a lot of photons. So we had to sit there very slowly with the detector, get a nice average value, and then move to the next wavelength and let it adjust, and then move to the next wavelength and let it adjust. So we were just letting a little bit of light through at each wavelength. And so the scan took about 35-40 minutes. So that's another reason why we don't really go sit in the lab for 35-40 minutes and let this box do its thing. Okay. I mean, it's wasting everybody's time, and essentially you have a little gas cuvette. Maybe I should bring at least the iodine in the cuvette. You could see the sample. And so this is what we're doing for very small molecules. We can resolve those vibrational lines at least. And so that's what we see in this spectrum. We have the ground electronic state and the excited electronic state, and then we have those vibrational wave functions. And if we were to multiply those wave functions by each other, and then integrate overall space, we would get what we call the overlap integral. And you can see where this ground state here is tall. It lines up with where this wave function is tall. And so that integral, the result of that integral, is what we call the Franck-Condon factor. It's very similar to the transition dipole moment integral, but we just don't have that dipole moment operator in the middle, the x-axis. So this is really just looking at the wave function pieces. You may say, well, this wave function is large over here too, but this wave function tapers off. You see it goes down to 0, and so essentially over here, there's no overlap. This wave function is equal to 0, and this wave function has got a large amplitude, but there's really no overlap over here. It's this area where you have this Gaussian curve. The ground state wave function for vibration is a Gaussian curve, and that Gaussian is overlapping with all of these vibrational levels here. And so that's what this Franck-Condon principle is. It's those vertical transitions. We're going from that ground vibrational state, straight up into the electronic state. And so that's what those intensities are. They're governed by the Franck-Condon factors. And so here's that gives us this absorption spectrum that has a maximum that's not necessarily the 0 to 0. And this was part of our last exam. We had that overlap of the absorption and the emission spectra. And this, if you kind of look at the shape of this curve here, of course it's in wavelength, but if you were to plot it in terms of energy, the shape of this would be sort of the shape of a Gaussian curve. And that would be the shape of that ground state vibrational wave function. And then all of the individual peaks under that, what we call this envelope, under that envelope, would be the overlap integrals with the upper state wave functions. And so that's what you would have for those individual intensities, where here the 0 to 4 has the largest intensity because it's directly over the center of that ground state vibrational wave function. And so this would be our ground state bond length, and then to longer distance here, this is the upper state bond length. If we were to extend that down, I can't draw a straight line on this tablet, so just imagine with your brain here that this drops straight down to the x-axis, and that gives you the bond length for the excited state. And so I'll just do RGS is the bond length for the ground state, and REX is the bond length for the excited state. So in our experiment, we're going to have two vibrational frequencies that are related to the different potential energy surfaces and different force constants, one for the excited state, one for the ground state. So we're going to be solving for those vibrational frequencies. Because we don't get the rotational lines, we will not be able to solve for the bond lengths. Okay, so we'll just be missing that piece. Now, if we have high resolution, we can resolve those vibrational transitions, but for low resolution, we just see some bumps occasionally in the UV-Vis spectrum. Now, let me talk a little bit about this way of assigning spectra. This was in the exam. I just showed it to you in the exam. I didn't ask you really to interpret it, but you probably saw this little line, this horizontal line, and all these vertical lines in those spectra in the exam. And what that was showing was saying these are all the transitions. They start in the V double prime equals 0 state. So that's down here. V double prime equals 0. So they're all starting there, and then they're going to these V prime levels. So this is the 0 to 0 transition. This is the 0 to 1, 2, 3, 4, and you see 5 here. So it's just kind of like a little ruler showing you the assignment of that spectrum. All of these have the 0 state in common in the ground state, and they're going to different excited states. Of course, at low resolution, you wouldn't be able to see all of those. You might be able to assign a few of them. Okay, but there may be one here, but it would be hard to tell where that 0 one is going to be. And so if you don't have the 0 to 0 transition, it's hard to know which one you're on. And so without high resolution, it's just difficult to assign the spectrum. So what we would do in that situation is we would do our best effort. We would assign the bumps that we see, and then we would see if that makes sense with other data, vibrational data. And then we say, no, that must not be the 0 to 0, that must be the 0 to 1, because that matches the other data that we have. And so actually deciding on where these peaks are, which quantum numbers are, is something that's pretty difficult. And so for your lab, you're going to be given the key, okay, because there's some debate about, which is the best model and so on. So you're going to be given the key, but just understanding the key is pretty difficult. So we're giving you enough to chew on. We're not giving you too much to chew on, okay? So when you wonder where these numbers came from, they were just given to you, okay? So it's not obvious that the peaks that you're assigning are those numbers, okay? I'm just giving you the key, and you are applying it to your spectrum. Okay. And so here we have those various transitions. Now let's look at the rotational levels. So down there on the vibrational levels, we have the P and R branches. Now, if we were to resolve them, this is what they would look like. Because we have such a longer bond length here, what does that mean for B? B is... If the bond length is longer, where is it? Is it the numerator or the denominator of B, the rotational constant? Yeah, and if you can't remember, you can think of it just like an energy equation, right? If the size of the system gets larger, what happens to the energy level spacing? It gets smaller, yeah. So it's in the denominator. So B is smaller. And you can see that up here. You see the spacing and the energy levels, they're smaller than down here. So this has a large B. The spacing in those levels is further apart. And so whenever you have this dramatically different B, you have a different rotational constant in the excited state than you'd have in the ground state. And so if you noticed in your P and R branches, for carbon monoxide, the P branches got further apart, spaced further apart, and the R branches got closer together. It's very slightly, but they did. Okay, they weren't exactly even. And what you have, and that's because the upper state, even in just 2 vibrational levels, the upper state B value was just a little bit smaller than the ground state B value, just a little bit. And that was enough to cause the peaks to shift to lower wave number values. You also had subtractive term for centrifugal distortion and other subtractive terms. In this case, the B is dramatically different, that the P branch lines drop off and get further, to longer wavelength values, and then the R branch actually folds back on itself. So what's being shown here with these arrows, the reason these fold back on themselves is that's kind of what we see in the absorption profile. So the P branch lines go up like this, and then they get further and further apart, right? And then the R branch lines go up here like this, and then they turn around. And so then the R branch lines go like this. So both the P branch and the R branch lines are not resolved, and they go, the intensity, when you average all that intensity, this is the shape of the peak. It's an asymmetric peak. Now, if we were simulating this spectrum, what peak shape would we use? Little review question here. Okay, we have several options. We have the Gaussian, the Lorentzian, the Voigt, which is a combination of Gaussian and Lorentzian, and the log normal. Yay, very good. Okay, so it's our little Kahoot for the day. This would be, you could use a log normal. Log normal line shape, tailed to the long wavelength side. Now, depending upon temperature, depending upon vibrational level and so on, this peak maximum is somewhat variable from one end of the spectrum to the other in the way it relates to the center of that band. Okay, so right here you have the center of that band that's from the vibrational level, P double prime 0 to 1 or something like that. And so what we're trying to find is this location right here. And in the past, we've always peak picked the maximum value. So I need everybody to really focus on this. We used to peak pick the maximum value, but in this particular lab, they said the error is smaller if you pick the minimum. See how this peak goes up and then it comes down and then it sort of ends there. This is the spot we're peak picking because that's closer to the actual transition. And plus, it's a little bit more identifiable place than the peak maximum, because the peak maximum is flat, and you have a lot of uncertainty there. Now, you can find the actual data point that's the maximum, but this, because there's a change in slope, a dramatic change in slope, it's a little less ambiguous too. So we're trying to find this place, and the closest thing we can find to that place reliably is this spot right there. So that's the spot on the short wavelength side. We're picking this where the line's coming down, and as soon as it changes slope, that's the spot we're picking. Okay. That's just what we're doing. All right, was the suggested spot to pick in analyzing these results. Once again, people have analyzed the results using different techniques, and this is the technique that gives the best values. So we're kind of standing on the shoulders of giants there. And so since we have asymmetric peaks, this is just in text what we're talking about. And so those are called band heads, those asymmetric peaks. And so we're picking that spot on the short wavelength side of each peak. Okay, so here's the iodine potential energy diagram. It looks very similar to the oxygen one that we had last time. And these are all of the different values that we're going to see here. We've got the electronic states. We're going from the X state to the B state. Those are the identities of the electronic states. We have those potential energy surface curves. We have the vibrational wave functions, and we have the vibrational energy levels. Now, iodine is a big molecule, so the big heavy masses, because mass is in the denominator of the energy equation, means that the energy levels are close together. So that means in room temperature, we're going to have some iodine molecules that are in the V equals 1 and 2 states. So our thermal population, we've got a lot of iodine molecules in the V equals 0 state. Let's say we have 5 there, then we might have 3 there and 1 there. So we have sort of an exponential drop off in terms of the population of those levels. But that confuses our spectrum, because then we have peaks that go from 0 to 14, from 1 to 14, and from 2 to 14. Right? Because we have molecules in all of those spots. And then we also have, other levels up here that they go to, but I'm just showing 14 here. And so we have a lot of overlapping spectra. So we have 3 series of peaks. These are the equilibrium bond lengths. Again, the double prime is the lower state, the prime is the upper state. This is the electronic energy difference, nu EL. That's one of the terms that we're going to solve for. And then we have the bond energies, so those dissociation energies. And then we have this atomic excitation. So this is just that energy difference between this excited iodine atom and this neutral iodine atom. Okay, so does everybody at least understand the potential energy surface diagram? This is a good mental image for you to have. This is the energy level diagram, and then we're going to go to the spectral lines. Remember, the spectral lines are the differences in this energy level diagram. Okay, so here's our energy level diagram on the left, and we flip that on its side. That's where we kind of see the spectrum. Okay, so we're looking at differences between these. So here I'm showing the 0 to 14 line and the 0 to 15 line. And so if we're scanning the monochromator along, when we get to this point, we're shooting light in there and it's hitting that iodine molecule, and we have an absorption. And that absorption is connecting V double prime equals 0 to V prime equals 14. We scan a little further, and we get 0 to 15. But on top of that, if I had an arrow that was, like, say, right in between, it might be the 1, let's say, to, I'll say 16. We might have one here that is this guy, the V double prime equals 1 to V prime equals 16. So it went 14, and then there was a 16, and there was a 15, but that 16 is the 1 to 16 line, and the other two are the 0 to 15 line. And so we have some alternations in these different spectra as they overlap each other, because the arrows are the right length. So the monochromator doesn't know which transition. It can't do the 0 series and then go back and do the 1 series, because it's just whatever length of arrow that monochromator is sending through our sample, it could absorb. Okay. So that's what complicates our spectrum a little bit. And so so here's the terminology that we're going to be using in the iodine lab. We have 3 different types of energy equations, and so we've given them different letters. We used to use E for everything, but now just in this lab, and it's in the Nibbler handout, that's where these terms are coming from. T is for the electronic states, G is for the vibrational states, and F is for the rotational states. And since we can't resolve the rotational lines, we're just going to take this right here. That's the electronic transition. Okay, so that's the difference between the electronic transitions, and then we just have those vibrational states, the G of V's. So substituting in the energy equation for vibration, and we have the anharmonicity constant here. And so we're going to include anharmonicity because, again, we have a huge molecule and a very anharmonic surface. So those energy levels are not constantly or equally spaced because of anharmonicity. We get this transition equation in wave numbers. So we have one of these for the ground state, here, and then we have another one for the excited state. And so how do we keep them straight? We put double primes on one and we put single primes on the other. And so here's this long equation, but it's not too bad if you think about it. It's just the vibrational motion plus the electronic difference. So we have single primes for the upper states, and we subtract the lower states, the double primes. So it's straight energy equation, upper state minus lower state. The trick is assigning the spectrum. Once you assign those V quantum numbers, the upper state and the lower state V's, then you do a linear regression, and here's your columns. So just like we had those linear regressions for carbon monoxide, which were related to the M's, which were related to the J values, here we assign the V primes and V double primes, and once we've done that, then we set up this regression. So our columns are V prime plus a half, V prime plus a half squared, V double prime plus a half, and V double prime plus a half squared, and that's it. We do the regression on that, and we get our vibrational frequencies for the upper state, which would be the new primes, and the lower state, the new double primes. And so here's our spectrum. This is the UV-Vis spectrum, really just visible. It's 500 to 700 nanometers. And you see all of those peaks. Those are the vibrational motions, the vibrational levels in iodine. And you're going to assign every one of them. It's not that bad, okay? But we got to find a way to start, right? Because it gets noisy down at this end, it gets noisy down at that end. So we're not going to start at one end or the other. We are going to start where this funny little pattern happens. It looks kind of like an interference pattern here in the middle. And so this is the key that I was telling you about. You're going to get this key right here, and this is the key right in this lecture. So do you see where it goes high, low, and then it's kind of even, and then it goes low, high. So that's the spot you're looking for in the spectrum. And when you find that spot, then these are the assignments. Okay, you can start with that minimum. So on the short wavelength side, so this is the short wavelength. So this peak right here, this band head, that peak right there, we go to the short wavelength side, we pick that spot, and that is this one right here, which is V double prime equals 1, and then this is 20, 21, 22. So that's 22. So that spot right in the middle is 1 to 22. It's starting out in the 1 state, down in the ground electronic state, and going to the 22nd vibrational state in the excited electronic state. Okay. And then notice to the left and right are coming from the V equals 0. So let's go to the left. This band head position here, if we pick on the short wavelength side, that spot right there, that's the 0-20 transition. So it's starting in the V double prime equals 0 and going to V prime equals 20. And that difference is very close to the difference between 1 and 22. So again, it's just scanning light through there, and whatever transition lines up with that particular frequency of light, it gets absorbed. And then you can go, you can just keep going. The next blue one is the 1-23, and then you have the 0-21, and so on. And you just start assigning those spectrums. So what you'll do is you'll pick that point, you'll set up your column, you'll have a 0 column, which is your V double prime column, you'll have a V prime column, you'll call it 20, and then you'll come down here and get the wavelength. You know, you hover over it and you get the wavelength, and you paste that wavelength in. You can do it in the table if you wish, or you can do it from the chart, whichever way you want to do it. And then you'll convert that whole wavelength column to wave numbers, and we'll do the analysis in wave numbers. But you'll peak pick your values in wavelength because that's what the spectrum is in. The questions so far. This is the critical piece here, is assigning the spectrum. Once you get the quantum numbers and the frequencies, it's linear regression is pretty easy. Okay. Yes.
Do we have to do our own? You give us the key. Are we expected to go outside of this key, or just the values you give us?
Oh, great question. Yeah, you keep going until you hit the noise. So on either end, you kind of run out, and you're like, is this a real peak or not? You know, and you use your judgment there. Yeah, yeah. And so this is just the thing to get you started. And notice there's three series. There are actually other series in there, but let's just do the three that we have, the 0, 1, and 2 series. Yes.
So that right there, the iodine and that the first the set of lines there on the left.
Yes.
That's what we're going to be working with. And
yes, you get this.
What you're doing right there is kind of showing us what we're going to do.
Yeah, that's right. So this is the spectrum that you have. If you plot it, that's what it'll look like. And then you just zoom in on it and you find with the mouse which spot I want you to pick. Now, it's pretty weak over here. I mean, I can totally get if you don't believe that there's a peak here. Right? So this area here is the most difficult, right? Because I can see that this goes up, and then it tapers off, and then another one starts, okay? And then it comes down, and then it goes up, and then there's kind of a shoulder there. So, I would probably pick that spot right there. Okay, this spot right there. It's not, whenever, okay. And then there's this change in slope right there. That's like the weakest peak, but that's the first one of this V double prime equals 2 series. And then you're just kind of looking at where there's a change in slope. Definitely a change in slope here. There's a change in slope there. Okay, it goes over this. We're not picking the peak maxima, but right here there's a change in slope. And so we're picking that spot right there. Change in slope there. We go past the maximum, and there's this little hump. And so we're picking that. So these two or three are the most difficult ones to assign. Up here, there's kind of a little doublet, a little bump. And so you'll see that one. These are the ones that I think that people struggle with the most on the V double prime equals 2. The strong peaks are the V double prime equals 1s. It's these little weak ones that are the 2s. But once you get past sort of 14 here, then they're all V double prime equals 2, and they're easy to assign from this point down. Okay, so the V double prime equals 2 series is really hard to assign in this overlap region. Okay, and that's all right. Yes?
Is that where it's going to help us again to take like our x-axis and really zoom in on it?
Yeah.
To actually see those, and then also do the conditional formatting where we had the colors and everything.
Yeah,
it helped us to...
Because we're not picking the peak maxima, the conditional formatting won't be as helpful. Because it was able to give you the maximum. And here we're really kind of looking at a slope change.
Oh, so it doesn't work for reverse.
Yeah, so we're just getting a slope change. Now, you might be able to do a first derivative where you just take the differences, that cell minus the cell above it. And then you're getting a first derivative, which would detect some of these slope changes, but it would also be very noisy. So I'm not sure. I've never done that. If you want to try it, cool. But I would just have this zoomed up and get my magnifying glass out and look at my spectrum and say, okay, I think that's the point DW is picking there. Okay, and go through the analysis that way. Yeah.
So there's not a more efficient way to do that.
There's not really a more efficient way to do that. I'm sorry. Now, once you get to the wings, then you can pick the minima instead of the maxima. So then you can find those easily with conditional formatting. Like if I were to conditionally format this area here, then I would pick like the red spot instead of the green spot. If your green is low and red is high, I would pick that minimum in that region, and that would get the right one. Sound good? Yeah, so just this middle overlap region is the real difficult spot. Going left and right is much easier. Yeah. All right. And so, again, notice we're not picking the peak maximum. We're choosing the minimum on the short wavelength side of each peak. Okay, so once we have that, this is sort of the whole procedure. We import the data in Excel. We create an XY scatter chart. We expand the x-axis. By double-clicking that x-axis, you can change the limits. You hover the mouse over a bandhead position and read the x position. Then you assign the correct V double prime and V prime quantum numbers to the bandhead using that previous chart as a guide, and then you make the table with those columns of quantum numbers, wavelength, wave number, and then you're ready to do the regression. So have y'all imported data yet? Have y'all done the text to columns? Okay, I'm kind of out of sync then. I'm teaching you how to do it and you already know. Sorry. Okay, so you got the wizard here. If you didn't quite understand, and this is the wizard, you've got that. You select it all down. You can use that data, text to columns, pick delimited. This is super helpful too in other areas if you're even like looking at your bank statements you download. Okay, and if it's not broken up into columns, you can use this. Okay, the tab, and then you can pick your columns and inspect it, make sure it's giving you what you want, and then you hit finish. Okay, creating a scatter chart. Y'all have done that too, I think. But when you're doing Spectra, you don't want to use the markers. I think you discovered that, I'm sure. One thing I do that want to take the opportunity to say, though, is never use the smooth lines. Okay, I'm like kind of waging war against the smooth lines. It's not just my own pet peeve. If you put a line on any chart or graph, you need to be able to supply the equation for that line because you're providing a model. Okay, so you can have scattered data and you put a line through it. You better know the slope and the intercept, right? And if you've done a trend line, you can display those and so on. If you're using this spline function that's kind of putting a smooth line through your data, and I ask you, because I will, if you're giving a presentation, what's the equation for that line? You're going to be like, I have no idea. Okay, because that's some smooth spline fitting to your data. So don't ever use that. And not only that, it does some funky stuff. Like you'll have two sharp points here, and it'll go way past that and do kind of a loop, and it'll look terrible, and it's not an accurate spectrum. So that's just the way it is. And then for small data sets, you can use markers only. It is okay to use the markers with straight lines between the points occasionally, just to keep the data series straight, like if we've got overlapping data. But you know the equation for those lines because it's just 2 points. And if you're given 2 points, it's a linear line between those 2 points. And you could, with a little bit of algebra, tell me the equation for that line if you knew the 2 points. You have to go back to your 8th grade algebra. But you could do it, I'm sure. I'm confident. Okay, so you, again, expanding the x-axis range, you click once on the chart, double-click the x-axis, and you get these tools here where you can change the minimum and the maximum. And then you can zoom in on that bad boy. Now, if you zoom in too much, it may be hard to see where the slope is. So this would be a good zoom. We get 2 or 3 or 4 peaks on the screen, and then you can hover over that. When you hover over that, you get this 559.5. And so then that's the first one you can assign. That's the V1 to V prime 22, and that's the wavelength. So you would type that down. Okay, there's only 4 significant figures in this x-axis, so you could probably type these. For the wave number values in the infrared, no, there was like 7 or 8 figures, and you're going to transpose some characters and screw that up. These, it should be pretty easy to detect if you've transposed one of these characters because they're all significant digits. Okay, so this is all pretty straightforward. And then once you have the assignment table, you convert that wavelength to wave number, and then once you have these wave number values and the quantum numbers, you're ready to do the regression. You create in the 5th and 6th columns, in 7th and 8th, the V prime plus a half, V prime plus a half squared, V double prime plus a half, and V double prime plus a half squared. And then those would be your X inputs for the regressions. This would be the assignment table for your lab report. And then the Deslandres table. This is how you detect if you've screwed something up and picked the wrong spot, okay? It's kind of a tedious table to make, but it's really helpful, and you want to include this in your report. So what this has is kind of a busy table. You have across the top, V double prime equals 0, 1, and 2. And then down the side, you have V prime, and you have all those levels, 12, 13, 14, 15. And so the 1 to 15 wave number value is here, okay? The 1 to 16 is here, and this is the difference between them. So this is the vibrational frequency, okay? And then the 0 to 16 level is here, and so this is the lower state vibrational frequency. This is the 0 to 16, this is the 1 to 16, and so you see the difference between those is that 0 to 1 difference. So this whole column here between 0 and 1, This column here is the ground state vibrational frequency from 0 to 1. And then the 1 to 2, this is the ground electronic state vibrational difference or vibrational frequency from 1 to 2. And then this difference here, 106.7, that's the difference between 12 and 13. 105 is the difference between 13 and 14, and so on. And so we can kind of see these differences. And what we're looking for is really kind of a smooth progression here. You see this is 96, 98, 97, 98. It's going up as we go up, these differences. You see this one, and this one, and this one, and this one. But notice how we have kind of a low value here and a high value there. That kind of makes me think that this peak assignment might be a little to the long wavelength side, like it might not be perfect. Okay, I went back and looked. There's really not a better answer for this one. You know, it's just not a very easy one to assign. It's that 2 series where it's overlapping. But if you have a huge, like if this was like 40 and 150, you see it's way out of the trend, then that can sort of alert you that you've made an assignment that's wrong, or maybe you transposed a number when you copied it down. Okay, so this is a good table to help you find mistakes in your assignments. Yeah.
So you would recommend doing this before the linear regression?
I guess if you did the linear regression first, and I guess you may be able to detect mistakes with your linear regression if they were dramatically bad. Okay, but if you just had one peak out of whack or two, it might not throw the linear regression off that much. This would just help you get the best linear regression possible. So yeah, I think it probably makes sense to do this before the linear regression, just to try to detect if you've made any major mistakes. Now here's what it's saying: separate your transition frequencies into your 3 columns, 0, 1, and 2, and then you can just drag those columns apart and then paste in the cell, like you've got some formulas in here. You've got E6 minus E4, okay? And then you copy that down, and then it's E8 minus E6, and so on. So you just, a lot of copying and pasting. So you're going to get familiar with the Control-C, Control-V, right? Control, copy once, and then Control-V, down, down, Control-V, down, down, Control-V, down, down. And you can do that pretty quickly. Yes?
So you were explaining that kind of like with the row vibrational, we did that. The R and the P.
Yeah, we had that plot. Mm-hmm.
And you could see kind of where you might have messed up with the peaks. Mm-hmm. And so you're saying this is kind of similar to that?
It's kind of similar to that. And you might be able to plot a similar thing with your V's. Like you might have, I don't know that, I mean, that's not required for the lab, but if you wanted to plot the trend according to, say there was a plot from V equals 0. Yeah, there is. It's a Burge-Sponer plot. Yeah. So you plot your 3 series. The V equals 0 series, the V equals 1 series, and the V equals 2 series, and they do overlap. And you'll be able to see if you have some messed up transitions. So you have the frequencies on the y-axis, and across the x-axis you have the upper state quantum number. And then you plot the V equals 0 series of upper state quantum numbers, the V equals 1 series of upper state quantum numbers, and the V equals 2 upper state quantum numbers. And so you'll have those 3 overlapping linear, or not quite linear, but close to linear lines. And you'll see those.
What did you say your x and y axis were going to be?
The x-axis is your upper state, so your V primes. And so you're going to have 3 columns of those. You're going to have a column of V equals 0 column. See here, the V double prime equals 0 column. So without all these differences, if it was just the frequencies, you would have 14 in that number, 15 in that number, 16 in that number. And so you would plot these values, right? And that's the V equals 0 series. And then you would plot these same values for the V equals 1 series, and then the same values for the V equals 2. And that plot would be you know, a nice clean plot of wave number values versus each quantum number. And you would be able to tell if you've made a dramatic mistake, transposing numbers in particular. Yeah. Anytime you're copying numbers from one spot to another with your hand and your brain, you're going to make a mistake. I've ruined myself from remembering numbers. You tell me a phone number? No. I have to actually look at it when I type it down because I've told my memory you're unreliable. And it obeys. And now I can't remember any numbers from, So
what was the name of that plot?
Burge Sponer. Let me write it out. And it's in the Nibbler handout. So read through that. That's a really helpful tool. Okay, we've got very short time for the test. Okay, so let's go ahead and do that. Unless you want to spend more time next time. Well, no, Wednesday I'm going to be gone. So, ATS meeting. Okay. Rachel Alvarado. Look at it. Well, sorry. And we're missing. As soon as you done sort of looking it over, start bringing them up to me because we don't want to take up Norman's time. Oh, I'm sorry. The folks that had difficulty on the last one was really just, I think, probably just not thinking about it. You only had to deal with the last two electrons, You know, the S2, it's a fully filled subshell, so you're only dealing with the unfilled subshells. And so you had what was it, a D and an F? Oh, what? P and D, yeah. And so you're just dealing with one electron and a P, one electron and a D, and so then you start with L1 plus L2, and away you go. Okay, so just when you're done, go ahead and bring them up here. I'm going to start tearing down. They play around with the word nothing. You know, nothing is really no thing. Okay.
Did you change the due dates and stuff? I got an email saying things were updated.
I did update, like I did put a homework thing up. Let's see, what was it? Let me pull up Blackboard and just look to see. We kind of take an assessment here.
I thought everything was due on Wednesday, but you got a stack. You got things due the 5th. I'm like,
On the 5th, yeah, it's possible. Because I wanted to give you some time to do whatever it was. So let me look. And y'all help me out with who's at the ACS. I know, is Morgan at ACS right now? Who else?
I think it's just Morgan.
Okay. All right. I had to change my password. It's so hard to remember. You know, it's like, it's too frequent. You know, I mean, I think it's a good idea, but in the middle of the semester, come on.